Today we are going to discuss shrinkage in plastic injection molded parts, specifically fiber-filled materials and the anisotropic shrinkage behavior. Understanding how parts shrink, especially, when they have these fiber fillers, it isn't just some minor detail. It's absolutely critical for producing high-quality functional plastic components. Get this wrong, and, well, you're looking at significant headaches down the line. So let's jump right in. What's the fundamental difference between uniform and this anisotropic shrinkage in injection molding? And why does this distinction matter so much?
Right. Well, most people might picture a part just getting uniformly smaller as it cools, shrinking equally in all directions. That's what we call uniform or isotropic shrinkage.
Okay.
You typically see this in many unfilled amorphous materials. They shrink, sure, but it's a relatively small amount and pretty much uniformly everywhere. It's, let's say, predictable.
Predictable, right.
Exactly. But anisotropic shrinkage, that's where things get really interesting and, frankly, more complex. It means the material contracts at different rates depending on the direction.
Different rates. How does that work with fibers?
Yeah, so in fiber-filled resins, this happens because of the alignment of those reinforcing glass fibers during the injection process. Think of it like this. As that molten plastic, packed with tiny glass fibers, gushes into the mold cavity, the sheer force, the flow itself, it literally lines up those fibers, kind of like logs floating down a fast river, mostly pointing the same way.
Okay, I can picture that.
Now, here's the crucial part. Those glass fibers themselves, they don't really shrink much at all.
Right.
So they act like tiny internal reinforcing bars, like rebar in concrete. They restrict the resin from shrinking along the flow direction.
Ah, okay.
Consequently, the material shrinks much less along the flow direction
Yeah.
and significantly more in the cross-flow direction that's perpendicular to the flow.
So a big difference depending on which way you measure.
A huge difference. For example, take a 30% glass-filled nylon. It might shrink as little as, say, 0.3% in the flow direction.
Wow, tiny.
But then as much as 1.0% in the cross-flow direction.
That's more than triple.
Exactly. And we see this consistently in material data sheets. Take a 20% glass-filled PBT, molding shrinkage parallel to flow, typically around 0.40%.
Sure.
But shrinkage normal to flow can be 1.20%. Again, 3 times higher. It's a fundamental behavior of these materials.
That really highlights the difference. So if a mold designer overlooks this directional shrinkage, and just applies a single, average, uniform shrinkage value to a fiber-filled part, what happens? What's the real-world impact?
Oh, it's detrimental. Ignoring anisotropic shrinkage isn't just a minor error. It's practically guaranteed to cause problems. It builds defects right into the mold design.
So the part just won't be right.
Exactly. The part simply won't shrink properly, and it will most likely never meet its dimensional requirements. This leads directly to major defects like severe warpage and distortion.
Warpage, like bending or twisting.
Precisely. The differing shrinkage rates create these internal stresses that cause the part to bend, bow, or twist out of its intended shape. Critical dimensions won't be held, so if your part needs to fit accurately with other components, forget it. It becomes functionally unusable.
That sounds like a nightmare for assembly.
It is. And on top of that, this residual internal stress can compromise the part's mechanical strength and its long-term durability. It can lead to premature failure in the field. It's truly a recipe for disaster if you don't account for it properly up front.
That makes perfect sense. So knowing how destructive ignoring this can be, how do tooling and design professionals actually deal with it? How do they compensate effectively? What are the strategies?
Right, so this is where advanced tools and really careful planning come into play. One of the primary methods is using specialized software, things like mold flow analysis.
Simulation software.
Yes, exactly. This software can model the entire injection process. It predicts how the fibers will orient themselves based on the mold design, the gate location, the processing conditions, and from that, it predicts the resulting anisotropic shrinkage and, crucially, the potential warpage.
So you can see the problems before cutting steel.
Precisely. It allows designers to visualize and correct for potential warpage before the expensive tool is even cut. And it's fascinating because, the fiber alignment isn't uniform through the part's thickness. Near the mold walls, you get high shear fibers aligned with flow, but deeper inside, the flow is different, and fibers can orient differently, sometimes even perpendicular in certain layers. It's that complex layered structure that simulation helps predict.
Okay, so simulation is key. What else?
Well, tool makers also directly adjust the mold dimensions. They actually build the mold cavity slightly differently, applying different shrinkage compensation factors for dimensions parallel versus perpendicular to the expected flow direction.
So they bake the compensation right into the tool geometry.
Correct. Another key strategy is optimizing gate locations. Where you inject the plastic has a huge impact on flow patterns and thus fiber orientation. So careful gating can minimize shrinkage variation. And for very complex parts, sometimes you really need prototyping and testing. Build a prototype tool, measure the actual shrinkage and warpage, and then use that data to fine-tune the final production tool design. Ultimately, it comes down to understanding all the factors. The material properties, obviously, but also wall thickness. Uneven walls cause uneven cooling and shrinkage, and the processing parameters themselves. It all plays a role.
It sounds like a very integrated approach is needed.
Absolutely. You need simulation, smart tooling design, and careful process control. And this really raises an important point, doesn't it? Considering these hidden forces of fiber orientation and directional shrinkage, you have to wonder how much more precision and foresight could we integrate into product design if we truly leverage these advanced analytical tools right from the very beginning.
That's a great question to ponder, really pushes the boundary of design thinking. If you have a new project, reach out to True Position Plastics. Justin and his team can help you with DFM, mold flow analysis, mold design, final molded parts, and consulting needs. You can contact them at www.truepositionplastics.com.